Hi, Pre-Calc 12s. Today we're going to take a look at rational functions. Rational functions is a little bit of an extension from Pre-Calculus 11. There will be some new things that we're going to take a look at today, but for the majority of this, this is something that you may have seen from parts of Pre-Calc 11 already. So just as a refresher, in terms of our definition of a rational function, a rational function is basically a polynomial divided by a polynomial where our denominator does not equal 0. So here's some examples of rational functions. We want to make sure we put a y equals or an f of x equals in front to indicate that we have a function. And we could say it's something like this, 3x plus 4 over x minus 2. There's a binomial divided by a binomial. That would be an example of a rational function. So quickly, here's a couple more examples of some polynomial functions. You could have things of different degrees. You could actually even have something where a polynomial, remember, could have something where you have an irrational coefficient. Okay, and so there's some examples of rational functions. They would all fall under the definition of being a polynomial divided by a polynomial. So if you wanted to see a couple examples of some non-rational functions, that could be something like 2 to the power of x plus 1 over x plus 3. So we know we couldn't have something where our exponent is a variable, or if you had something where your exponent was maybe underneath a radical, and this wouldn't be a polynomial at all. If you had x squared plus 3x plus 11 over x minus 4. Let's see if there's any other examples we could think of. What if you had something like this? X to the power of 1.5 plus x over 3. So for all of these reasons, we have some examples that make something not a rational function. Okay, so to see our understanding of this, let's see what we could do now to extend this and apply some of the concepts that we learned from Pre-Calc 11. So you've heard of an asymptote. So as a refresher, an asymptote is a boundary line that you get very close to and you approach, but you never actually reach. There's lots of examples of asymptotes that we're going to take a look at here. And specifically, we're going to look at vertical asymptotes and horizontal asymptotes. In this course, we're not going to study oblique or slanted asymptotes, but we know that that's also something that, that could exist. Think of something where, well, let's actually just go through what an asymptote is. If you were to graph y equals 2 to the x, and this is an exponential function. So this is not an example of a rational function, but it is something that would have an example of having an asymptote. So if I had something right here where I was to graph y equals 2 to the x, and I start putting in, let's say 0 for x. If I put in 0 for x, I would get 1. And if I put in 1 for x, I would get 2, 2, and 3. So as I start putting in more numbers for x, I would get something that would grow very rapidly. But what would happen if I put in some negative numbers for x? If I put in something like -1, -2, -3, 2 to the power of -1 would give me 1/2. This would give me a quarter, and this would give me an eighth. And you would get something here in which no matter how negative the values I put in for x, it's still going to create something that would have an output, a y value that's going to be a positive number, even if it's a very, very small positive fraction. And so if you were to graph this, you would get something that would look like this, and it would never ever hit the x-axis. It would approach it, and you would get very close to it, but you never reach the x-axis. And so we're going to say right there, you would have what we would call a horizontal asymptote. And we're going to denote that by having a dotted line, and the equation of that horizontal asymptote would be at y equals 0. So hopefully that gives you a better idea of the concept of what an asymptote is. For these next examples here, they're saying, can you find the vertical asymptotes for each of these 5 examples? So I'm just going to erase what we have here. Now, we know that, as a refresher, we focus so much of the year on non-permissible values, and that's when you have a denominator that would equal 0. And so if you take a look at some of these examples, you could say, can I factor these denominators, and then what would be my non-permissible values? So looking at this right here, I could say this would be x plus 3, x minus 3. Knowing that if x was ever equal to negative 3, or if x was ever equal to positive 3, I would create something that would be an impossible situation. I could never have that because I would be dividing by 0. And what happens though, if you take just one of these two examples, say x equals 3, is I could sub in 3.1 or 3.01 or 3.0001. I could put in any number that is just slightly above 3, and that would be okay. And I could put in any number that's slightly less than 3. I could put in 2.9 or 2.99 or 2.999, but I could never substitute in 3 for x because I would be dividing by 0. And so what ends up happening is you create something where you approach the value of x equaling 3, but it never reaches 3. Just like you approach negative 3, but you never reach negative 3. And so for those reasons, you would have vertical asymptotes at x equals 3 and x equals negative 3. So for the majority of these examples right here, you can just take a look at them and say, can I factor this, and then what am I left over with? Here I take out an x squared, and I'd be left with x minus 4. And so there, I would have an asymptote at x equals 0 and x equals 4. Now, I'd encourage you to take out your graphing calculator and to put some of these in for y1 and see what it looks like. And you'll notice that you'll have these vertical gaps. It's not going to show you a dotted line there, but you'll notice that x never does equal 3, even though it gets very, very close to it. Let's complete these right now, and then after that, let's take the graphing calculator and we'll look at one of them in a little bit more detail. Okay. So hopefully, hopefully you're getting the same thing for these vertical asymptotes. For part E, that says x squared plus 1. So it's representing an example of a sum of squares and not a difference of squares. And because of that, the denominator isn't factorable. In fact, you could put in any number you want for x, and you would never ever be able to make your denominator say 0. And so because this is a sum of squares, we're going to say that this does not have a vertical asymptote. If you said x squared plus 1 and you made it equal to 0 and you wanted to solve for x, you could always subtract 1 to the other side, square root both sides, and you would have the square root of negative 1, which is a non-real numbers. And because of that, you could say there's no solution for that. There would be no vertical asymptote. Okay, so let's explore just what these vertical asymptotes look like. And let's take a look at A. And I want you to put this in for y1 on your graphing calculator. So I'll give you a minute right now, get that out there, and see what you can see from that. Okay, so let's graph x squared over x squared minus 9. Let's just double check, see that's what we had. Oh, sorry, it's x over x squared minus 9. So if we wanted to graph that, we could do this two ways. If you want, I don't know if I've shown you guys this before. If you press something like alpha y, and then you select the first number there, then what that does is that creates a fraction right away for you. Then you don't have to worry about the way you bracket things. So alpha y, so x and then we can go down here and we're going to have x squared. So let's go x squared minus 9. And let's hit graph and let's see what happens. Okay, so from there, if you were to look right here and you count -1, -2, -3, you can see that right around here at x equals -3 and at x equals +3, you're going to have something in which your values get very close to it, but they actually never ever hit x equals -3 and x equals +3. And so that's representing our vertical asymptotes for that question right there. Okay, so continuing on after we've looked at some vertical asymptotes, now let's see what we could do with horizontal asymptotes. So for horizontal asymptotes, there are 3 potential rules that we could learn and then memorize, but I would rather us try to understand the concept just a little bit more. And this is going to be very important as you head into calculus for next year. If you have something like y equals 2x over 3x minus 1, and they're saying, well, what's the horizontal asymptote? What values do they approach but never hit horizontally? We can think about what would happen when you put in extreme numbers, so very large numbers or very small numbers. Let's take a look at what we mean by that. If you had something like 10, now 10 is not really an extreme number, but if you had something like 10, and you put 10 in for x, you would get 20 over 29. And 20 over 29 would be something that's just less than 2/3. Okay, 20 over 30 being 2/3. And so I guess it would be technically just more than 2/3. But the 29 is just off from the 30. If you picked a number like 100, you would get 200. Sorry, if I put in 100 here, you would get 200 over 299, which again, 299 is just less than 300, so it doesn't quite hit 2/3. And if you did that for 1,000, you could probably guess that that's going to equal something that again doesn't quite hit 2/3. In fact, there's no number that I could ever put in for x that would allow me to create a y value of 2/3. And that's because 2x over 3x would always reduce to 2/3, but I'm always subtracting that additional 1 that's at the bottom here. And so because of that, what we can say is I'm going to have a horizontal asymptote at y equals 2/3. What you can do then is you could say, if I take the leading coefficients of each other, and I say, well, what would happen if they're of the same degree, like we have right here, then I can just divide the leading coefficients by each other and I'll get my 2/3 solution right there. And so if that first part was a little bit strange, it's pretty easy just to divide the leading coefficients by each other. One thing I should add in here is up top here, this is saying as x approaches infinity and as x approaches negative infinity. So that's saying what's happening for these really extreme cases. Probably one thing you might be thinking of is, well, you chose numbers that are getting much bigger for a positive values of x. What would happen if you had negative values of x? Well, the exact same thing would have happened if I picked -10, -100, and -1,000. If I put in -10 for x, I would end up with -20 over -31, or -200 over -301, or -2,000 over -3,001. And so once again, it would get very close to 2/3, but we would never be able to hit 2/3. So let's take a look at what that would look like on a graph just before we continue on right here. So can you graph this for y1? Let's do this together, and let's see if we can see this 2/3 concept a little bit clearer by looking at it on the graphing calculator. So we have 2x over 3x minus 1. So for this time when I graph it, I'm going to say it's going to be 2x, and I'm going to put it as brackets, and I'm not going to use my shortcut, and I'll show you why in a second, over 3x minus 1. 3x minus 1. So if we graph this right here, it sure looks like that there might be a horizontal asymptote at 2/3. It's for sure something less than the number 1, but we might not be 100% sure what that looks like. But what we can do now is this. I didn't use the fancy fraction shortcut because if we go to our table of values, I want to see what our y values are as decimals. And if I use that fraction shortcut, it would have kept everything as a fraction. But what you can start to do is this. If you look at what's happening for some values of x as they become larger and larger and larger, take a look at the y values, and they get closer and closer to 2/3. So knowing that 2/3 would be 0.6 repeated, we're getting values that would get very close to it, but we never actually touch 2/3. And if you do the same thing here and you start to look back, well, what would happen if we had some negative values for x? And we would start to get values that would, again, they would be very close to exactly 2/3, but we never quite hit 2/3. Even if you had substituted in 1,000 or 1,000,000 or anything like that, we would never be able to get to those values. Okay, so from there, let's see if we can now answer our remaining 2 examples. Okay, so let's see what we have. Okay, so if we said y equals 2/3 for our first example, for our second example, I'm going to try to give you the answer a little bit faster, and then let's see what we could do with this. Right now, I have an x squared on the bottom. I have 1x squared on the bottom, and I have 0x squareds on top. And the rule from part 1 was saying if they're of the same degree, then we can divide the leading coefficients by each other, and that's going to tell us what the horizontal asymptotes are. And so because I had an x squared on the bottom and I had 0x squareds on top, if I divide those by each other, I would get y equals 0. And that would tell me that I would have a horizontal asymptote at y equals 0. And that will always be true when the denominator is of a greater the degree. So instead of trying to memorize these 3 rules, what I try to do is try to line up the leading coefficients and then just divide them by each other to be able to answer that quickly. So for example, with part 3 here, if we just try to answer this efficiently, if I have x squareds on top, but I have no x squareds on the bottom, you can write in that you have 0x squareds on the bottom. And if that's the case, now that we have them of the same degree, they're both x squareds, and we divide their coefficients by each other, we would now say it's 2 divided by 0. And 2 divided by 0 is undefined, and so that means that there would be no horizontal asymptote. So once again, what you could do with some of these examples as well is you could start to put in some extreme values and see what would end up happening, but you'll end up finding that for part 2, it's going to get very close to 0, and for part 3, you're not going to be able to come up with anything that you could trap as an asymptote. Okay, the next example then would be to be able to look at something in which we had a hole. You may have seen this in Pre-Calc 11, or this may be new. And a hole is something in which you have a gap, and it's not going to be represented by an asymptote, but it's going to be represented by something in which it's still undefined. And so if you have example 2, you always want to see if you can factor first. And if you can factor, let's see what we would be able to do to the top. You could say y equals x plus 2 x minus 1 over x plus 2. And you can reduce. you have entire x plus 2 factors that reduce, and you'd just be left with x minus 1. So if you were to graph this, it should actually look just like x minus 1 because the x plus 2's reduced with each other. And so quickly, if you're to graph your y equals mx plus b, we have a y-intercept of -1, and we have a slope of 1. Then it would look something, it would look something like this. So that's a slope of 1 with a y-intercept at -1. But there's one exception to this. If you were to identify the non-permissible values for this first question here, you would say, well, I think that x can't equal -2. In fact, we know it can't equal -2. And what would be the coordinate when x is at -2? It'd be at, when x is at -2, y is at -3. And you could confirm that because here, where you have your non-permissible value of x equals -2, if you sub that in, you would get -3. And so from there, we get the point -2, -3. And that's where we have something that is not allowed, but it's not an asymptote because they're not headed towards extreme values towards infinity or towards negative infinity. Rather, it's just a gap. And we identify that as a hole. And so if they want to say what's the coordinate of the hole, it would be -2, -3. And how did you find the hole? We factored our original, and wherever you reduce, the factor that you reduce, in this case x plus 2, produces a solution of -2. That's going to be the x value of the hole, and then you sub that in to your reduced form here, and you find the y value of the hole that goes along with it. Make sure that when you list the coordinate, you have an x value and a y value. Sometimes people just list the x value, and then you only get a part mark, and you know that when you have -2, -3, you want to get the whole mark. Okay. That was pretty good. Okay, so in terms of our vertical asymptotes and horizontal asymptotes, I don't think there are any asymptotes, and there aren't any asymptotes because this doesn't have asymptote type behavior. It doesn't head towards getting towards an extreme value and then not reaching it. It looks like a regular linear function. And so when you're trying to find your vertical and horizontal asymptotes, look at the reduced form. And by reduced form, I mean look at y equals x minus 1. Okay, so hopefully that question seemed reasonable. Here's a couple more examples that will help put everything together. Okay, so now we need to say, hey, can we find the vertical asymptotes? Can we find the horizontal asymptotes? And if there's a hole, can we identify that? Note that before we do anything, we want to always see if you can reduce first, because if you can reduce something, we know we would have a hole. So looking at part A here, let's always just factor and see what we could come up with to begin with. So you get x minus 3, x plus 2, and then sure enough, yes, the x minus 3's cancel out, so I'd be left with y equals 1 over x plus 2. So let's do the whole first. If we have something here, we know that we reduced something where x equals 3. And so from there, if I take 3 and I put it in for x, I would get 1 over 3 plus 2, so I get 1/5. And now if I want to identify the asymptotes, I still have a denominator of x plus 2. So I know that x could never ever equal -2, meaning I have a vertical asymptote at x equals -2. And if I want to find the horizontal asymptote, I have 1x on the bottom there. I have 0 x's on top, and if I divide the leading coefficients by each other, I would get y equals 0. So we have a horizontal asymptote at y equals 0 as well. For part B, if we factor this question is actually going to be a little bit easier. We're just left with y equals x minus 2. And for x minus 2, that's a linear function. There is no denominator that would give us any asymptotes, and we wouldn't have to worry about that. So right away, we actually know we have no asymptotes, horizontal or vertical asymptotes, because it's just going to be a linear function. But we did cross off something in which we were worried that we had a non-permissible value at x equals negative 4. And so we could say at negative 4, we could put in a negative 4 right there, and we get negative 4 minus 2, which would be negative 6. And then from there, that would be the point of our hole. For these types of questions here, you can always check back with your graphing calculator and see what that looks like, but hopefully that makes some sense. Okay, for here, we could factor x plus 2, x subtract 2. Factor out an x, and we'd be left with x squared minus 4. And then that looks like we could probably do a little bit more with it. So let's continue on. This actually could be a very interesting question, because on the bottom we would be creating x plus 2, x minus 2, which means that the x plus 2's cancel out and the x minus 2's cancel out, and we'd be left with y equals 1 over x. And so if we have something like that, think about how this would look. We crossed off 2 factors. And if we cross off 2 separate factors, that means that we have 2 separate holes. We have a double hole. Okay, so we're going to have something where we have a negative 2 value and we have a positive 2 value. When we plug in negative 2 right here for x, we get negative 1/2. And when we plug in positive 2 for x, we get positive 1/2. So there's our 2 holes. For y equals 1 over x, I know that x could never be 0. That would be one of my asymptotes. So we're going to say we have a vertical asymptote at x equals 0, and we have a horizontal asymptote at y equals 0, because we have 0 x's on the numerator, and so 0 divided by 1 will give us 0. So we'll have a horizontal asymptote at y equals 0. Make sure you get into a good habit of writing the full equation of the asymptote, writing x equals 0 or y equals 0. Don't just write something that would say vertical asymptote of 0 or horizontal asymptote of 0. You want to make sure that you're saying it's x equals or it's y equals. Okay, so we also have learned in the past how to find x-intercepts and y-intercepts, and we know that to find a y-intercept, we set x equal to 0. To find an x-intercept, we set y equals to 0. For the y-intercept, where we set x equals to 0, we could say something like this. If x was set equal to 0 for something like this, then we would say we would have 0 minus 0 plus 12 over 0 minus 4. We would just be left with negative 3. You can actually just divide the constants by each other right there, and we get y equals negative 3. So the y-intercept right here would be at negative 3. And the x-intercept, well, what would happen here if you said 0 equals, and then you had something that was like x minus 3, x minus 4 over x plus 2, x minus 2. Well, if I want to find out when the right side would equal 0, I am actually not concerned about the denominator. I could actually times both sides by x plus 2, x minus 2. And if I did that, it would still be times by 0 on the left side. So I'd be left with something that would say 0 equals x minus 3, x minus 4. and I would get x-intercepts at 3 and 4. In other words, when I want to find the x-intercepts, I can actually just look at the zeros of the numerator, and that's going to help me find that. Okay, for part B here, see how we could factor. Actually, let's find out, first of all, let's put in 0 for x. And if we did that, well, we would have something in which we would be left with -1 divided by 0. And so I think that in this case, there would be no y-intercept because I'd be dividing by 0. But if we wanted to find the x-intercept, then we could say 0, whoops, with y equals 0. We could times both sides by, actually let's factor it first. We get x squared plus 1, x squared minus 1 over x cubed plus 1. Now, in some courses, you may have learned how to factor a sum of cubes or a difference of cubes. We don't do that in pre-calc 12, so for our sake, we can actually just leave it as it is. It's not going to affect the question in any way. We times x cubed plus 1 onto both sides. And if we do something like that, we'd be left with 0 equals x squared plus 1, and then x plus 1, x minus 1. So we would have x-intercepts at +1 and -1. And those would be our two x-intercepts. Okay, we have two final questions here on finding the x and y intercepts. So because we've worked a little bit on this right now, why don't you pause the video and see if you can answer those on your own. Okay, so to find the y-intercept for our first one right here, we know we can just divide the constants by each other, and you'd be left with 9/2 as our y-intercept. And then for your x-intercept, let's see what would happen. Let's actually factor it first. So you could say x plus 3, x minus 3 over x minus 2, x plus 1. There's nothing we can reduce there, and that's why we like to factor it. And then we could put in 0 for y, times both sides by x minus 2, x plus 1. And we'd be left with the solutions on our numerator, which would be x equals -3 and x equals +3. And those would be our two x-intercepts that we have right there. For part D, I'm not sure if you worked ahead on this and tried to figure it out. It'd be very difficult to answer that question as it is right now. What we want to do is for each of the rational functions that we've had it as a single fraction. So I would recommend doing the algebra first to try to say, hey, can I get a common denominator? And from there, can I try to simplify it? So our lowest common denominator is going to be x minus 1, x plus 1. And so give each of the denominators whatever it needs to have a full x minus 1, x plus 1. For that 2 at the very end, you want to write that as 2 over 1, and you want to then multiply both the denominator and numerator by x minus 1, x plus 1. What you end up with then is you would get something that would say, well, you'd have a denominator of x plus 1, x minus 1, and then on top you would have x minus 1 minus bracket x plus 1 plus 2 times, and then it'd be x squared. The two middle terms would cancel each other out, so it'd be x squared minus 1. And we can actually clean this up a little bit more. So we could say k of x is going to be equal to x minus 1 minus x minus 1 plus 2x squared minus 2 all over x plus 1, x minus 1. The x's will reduce with each other, and we'd be left with now something that would say 2x squared minus 4 over x plus 1, x minus 1. We could factor out a 2, and we'd be left with x squared minus 2 and this would be one way of leaving it in a factored form to be able to help us solve our intercepts. So we'd have something like that. Or we also know that if we had left it in an expanded form, I'll just write this right here, we'd have 2x squared minus 4 over x squared minus 1. If we want to find out what our y-intercept is, we know we make x equals 0. And if we make x equals 0, then we can just look at these back constants that are being divided by each other. And if we did that, we'd have negative 4 divided by negative 1, which would leave us with positive 4. So we'd have a y-intercept of positive 4. We could have just as easily substituted that in here as well. And then to find our x-intercepts, this is a bit of a tricky one. We know that we could just look at the numerator and find the solutions to the numerator. Now, this is going to be, I'll go up here. Sorry, that's a little tight. We could say 0 equals 2 x squared minus 2, but then for the x squared minus 2, we could actually factor that, and you could end up with something that would say x plus the square root of 2, x minus the square root of 2. It's a difference of squares. And you would get something that would be negative root 2 and positive root 2. If you wanted to, you could have also said x squared minus 2 equals 0, add 2 to the other side, square root both sides, and then you create a plus or minus of that, and it'd be x equals plus or minus root 2. So in both cases, that should work, but regardless, those are the x-intercepts. That was a pretty tedious question. Okay, so here's the homework. There's lots of good questions to take a look at, and we could talk more about vertical and horizontal asymptotes at length in class 2. Thanks.